Yeah, sorry for the glitch. Let's continue. We are still on the drawing of the voltage time graph or current time graph. Voltage time graph for a DC generator, and then for the AC it will be, when we start from minimum, then it will be a sine graph. Those who know mathematics, this will be a full circle. In most of the cases, for the times here, if we don't use degrees, the times will be guided by the frequency. Let's say, for example, they say the frequency of the generator is 50 hertz. Therefore, if we calculate the period becomes 1 over frequency, which is 0.02 seconds. Therefore, it means that now for the full cycle it will be 0.02, and then this will be 0.01. If the frequency is given, be careful of that, because the examiner can catch you to say we are given the frequency, draw the graph, also show the time taken there accordingly, and then which means that now this one will be the maximum, if it's the voltage, maximum voltage that is produced by the generator, or the output of the generator. You can use the word output or maximum, it's one and the same thing. That is in a nutshell the two graphs. Be careful when we start from maximum and when we start from minimum, the difference there and the shape of the graph. Let's move to the next part of this section of electrodynamics, where now we talk about how do we increase the induced EMF now. So if we want to talk about the induced EMF, we are using, remember, Faraday's law. The Faraday's law, if you still remember from grade 11, we learned that the Faraday's law is talking about the relationship between the flux linkage, the rate at which the flux linkage now it's in a generator. So it's defined as the induced EMF in a generator now is directly proportional to the rate of change of the magnetic flux linkage, which is your delta, this one, Q multiplied by N, negative N, that's your flux linkage. Fine. So therefore, factors that affect the induced EMF, or ways of increasing, let me make it simple, ways of increasing induced EMF, ways of increasing induced EMF. One, according to the formula, will be we increase the number of turns, or alternatively increase the area of the coil, The second one will be use stronger magnets, so that the B will increase. Use stronger magnets. And now we know from this, phi equals to B A cos theta. Therefore, if we use the stronger magnets, we'll have the stronger field. Therefore, the EMF also will be affected. And then the last one is this one of increase the speed of rotation. Increase the speed of the rotation. In the wind turbines, the more wind, the more generation of electricity. Increase the speed of rotation. That's your delta T. Rotation in this case, meaning that if we cover, let's say, a full circle in 0.02, now will cover a full circle in 0.01. So the speed of rotation is increased there. Okay, and then let's talk about the direction. Finally, the direction of current versus rotation in a magnetic field in motors and generators. Motors and then generators. The motors, what do they do? Motors are using the Fleming's left-hand rule. Or they just oppose this one. The current and rotation oppose one another. That's very important and simple. We'll show you how it's applicable. Then generators are using Fleming's right-hand rule. Normally we say R in the generator. Can give you a guidance there, right-hand rule. Or generators here, the current and the rotation just follow one another. I'll show you how this is very easy to apply. I think so far we'll talk at the application of these two, and let's pause for now. Thank you.